Hello, and welcome to our Stanford University CS236 class project. We are very happy to present to you Accelerating Physics Simulation with Uncertainty Quantification. Our team members are Sang Trung, Arsha Head, and I'm the presenter, John Ngui. Simulation is fundamental to science and technology. Simulation provides a method of analysis which can be easily verified, understood, and communicated. However, engineered simulation can take substantial amount of effort and resources to build and run. Deep learning has been used to speed up simulation, but current techniques do not model the long-term evolution explicitly, hence prone to error accumulation. The lack of uncertainty estimation makes downstream decision-making challenging. We introduce active learning to train with significantly less trajectories. We sample initial trajectories that maximize model uncertainty and query the oracle to complete them. During inference, we use beam search to sample trajectories from the model, improving predictions for long-term evolution. Active learning and beam search improve density estimation and reduces error accumulation. We apply our method on the pendulum, two-body, and three-body problems. To the best of our knowledge, we believe that we are the first to attempt this in the physics domain, and that is very exciting. Now let's look at our methods. We use an autoregressive formulation trained with negative log likelihood and ensembling to estimate uncertainty. Given an ensemble of M models, the distribution of x t plus 1 is estimated by model as Gaussian. The uncertainty of the next time step can be broken down as follows. If you look at the math below, on the right-hand side, there are two parts. The first part is epistemic. The second part is aleatoric. We separate the training procedure into active learning setup with two steps. First, the model is trained on a standard dataset. A new dataset is created from a new set of initial conditions that maximize variance, passed through the simulation. At inference, for a single target input x, I to t, we use beam search to track a list of k particles. Below are two algorithms. Let's take a look at algorithm 1, uncertainty data collection. First, we initialize the simulator as a ground truth simulation. Next, we sample the data from the simulator. Then, we initialize the threshold. Here we train the ensemble f theta 0 from the dataset. Here we will loop through all new initial conditions given by d tilde I. In the loop, we pick the variance that is above the threshold and feed it to the simulator to produce a new dataset di. Then we fine-tune f theta I from f theta I minus 1 and the dataset. After, we increment I by 1. Now let's go on to the problem setup. Generative model generates forecasts faster than first principle simulators while estimating predictive uncertainty, enabling an active learning framework and beam search. Our goal is to train a generative model to estimate the dynamics of complex physical systems. Our other goal is to estimate model uncertainty to recognize when forecasts could drift from the ground truth. Here's our first setup. We set a dynamic system F that's mapped to 2D reals. We state X, where V and V prime are positions and velocities respectively. Due to uncertainties, we instead learn a model F theta that maps a history of states to a normal distribution. Then we test on the three-body, two-body, and pendulum problems. And here are our results. If you look at figure 1, model trained with a single trajectory has an average mean absolute error, or MAE, energy error of about 1.9 and the maximum MAE error of nearly 4. By adding the trajectory that maximizes the MAE to our data set using active learning, the model on the right has an average MAE error of below 1 and maximum error MAE error below 3. Next, let's look at Model 2. Models trained using the uncertainty-aware active learning framework show greatly increased training speed. Each bar contains 3 heights corresponding to the first, the second, and third epoch test loss in decreasing order. We initially trained models on the 3-body, 2-body, and pendulum problems for one epoch, then fine-tuned them using our method denoted in blue and random data points shown in red. On average, models trained using our method achieve half the test loss of those trained using random samples. This improvement is maintained with an increase in epochs. And finally, let's look at Figure 3. We tested our models on test data using both greedy search and beam search. On average, beam search shows marginally better performance. In conclusion, our experiments found that our method drastically improved training speed. On the 3-body, 2-body, and pendulum problems, our methods decreased test loss by nearly half compared to training with random data points. The use of continuous beam search slightly helps improve inference quality. By fine-tuning models on data points that maximize model variance, the maximum average error is greatly decreased. This is because the maximum epistemic model uncertainty is effectively decreased after fine-tuning. Aleatoric uncertainty theoretically cannot be reduced. Repeating this process allows for much greater sample efficiency, an important factor to reduce when training with data generated from expensive simulation software. Now let's compare to other methods. We achieve fast inference enabled by fast-forward pass of a deep neural network. The use of a generative deep neural network enables estimating model uncertainty with ensembling. The amount of training data is reduced using uncertainty-aware active learning. And finally, long-term evolution can be improved with beam search, and poor inference can be detected when uncertainty is high. For future work, while our method reduces model variance, in Bayesian methods, model uncertainty can be quantified in terms of entropy. We could also improve on the methods introduced here by using mutual information as an objective. We would like to spend the last few minutes to look at our code structure that helps simulate this project. Here is our code base showcased in Visual Code. Take a look at the left, which shows you our code structure. First, let's talk about the model file. Things to notice is the BLMP. Let's go there. That is our Bayesian multi-layer perceptron model, and the HGNS. That's our hierarchical graph neural simulator. We use these models for the pendulum and 2-body simulations. Next, let's look at the utils file. In here, we have greedy search and another function for beam search. And finally, let's look at the trainer file. We have one training loop for the regular learning, and we have another training loop for the active learning. The model, the trainer, and the utils files make up the core code base for this project. Thank you for taking the time to watch our poster presentation and a quick glimpse into our code base. I hope you enjoyed it, and feel free to reach out to any team members if you have any questions. Thank you very much.